Hi everyone, today we're going to be talking about the Poincare homology sphere, and to start, we're going to need some definition. So, here we go with definition. And remember that the three ball V3 is just a ball in three-dimensional space. And then our last definition is for a Hagar splitting. So a Hagar splitting of a closed three-manifold M, which is denoted in the following way. Right, M equal to H1 with this union with this S thing, H2, and this is a surface. S in our manifold M, which divides the manifold into two handle bodies, H1 and H2. And then here we call the surface S the Hagar splitting surface. So those are our last definitions that we will need. And then from here we can actually talk about the homology sphere. So one thing to note is that the homology sphere is a closed three-manifold, has the same homology as a three-sphere, but it has a non-trivial fundamental group. And Poincare created this space using a Hagar splitting and ended up getting a sphere with two handles attached. And we can think of this manifold as a pretzel. And to illustrate, we can draw Poincare's Hagar diagram. Okay, that's as good of a circle as we're gonna get. So we call this circle plus A. And then we have three more circles. This one is minus A. We have plus B, minus B. And then he draws a bunch of curves on this diagram in a particular way. So I will do that now. So we have 3, 2, 7, 6. So those are just points on the circle plus A. And we also have circles. We also have points on the other circles. So we have 1, 2, 3, 4, 7, 5, 6. We have 1, 5, 2, 3, 4. And we have 1, 5, 2, 3, 4. And then there's going to be different cycles corresponding to these points, which we'll denote by these arrows. So we connect 3 to 4, 2 to 3, 1, 2, and then 1 gets connected to 2 over here. And we have 1 goes to 5. And 5 goes to 2. And, oh, there's a 4 here. And 4 goes to 1. And then we also have 4 cycles, but now we're going to denote these with a dashed line to distinguish between these 2 sets of cycles. So we have 5 to 7. And then we have 7 to 3. We have 6 to 5. We have 4 to 6. And then we also have these other lines in here. So we have E prime, E, D, and B prime. And so we have that, and those two. So this going to E prime. And then we have this one going to E. And then that is it. Oh, there's also an arrow denoting we're going this way. And so that is his K-bar diagram. So to unpack this a little bit, so first, our surface is actually represented by a polygon. And the perimeter of this polygon is given by the 4 circles we have here. So we have plus A, minus A, plus B, and minus B. And then so each of the circles correspond to one of the other ones. So plus A corresponds to minus A, plus B corresponds to minus B. And together, those 2 pairings of circles form a cycle. And then the dashed lines, those represent another cycle, same with the solid lines with the arrows. And then these points, which we denoted with the numbers. So these are points that are on the circles. So if you're looking at this point here, that would be minus B1. And that circle would be identified with plus B1 over here. And we do that with the A's as well. So you denote, so you identify plus A, K with minus AK, and then B plus BK and minus BK together. And then one more interesting fact about the construction of the homology sphere is that there are actually 8 equivalent ways to construct it, so I'm not going to go into all 8.
Okay, so in order for this not to be a 3-month-long process of computing the fundamental group, we're going to use a different construction from the one that Brooke just showed. This one is using where each one of these disks, or each one of these nodes, sorry, represents a 2-disk bundle over the 2-sphere. And so we take 8 copies of those, and then we plumb them together, which is like connecting them in this very certain specific mathematical way. We plumb them together using this Daykin diagram. So 8 and 7 are going to be plumbed together, and any 2 nodes that are connected by an edge will end up being plumbed together. So once we have all of these 2 disks plumbed together, this is going to be a smooth 4 manifold. With a boundary. And we're going to call this boundary M. And luckily for us, our M is going to be a closed 3 manifold. And is also our construction of our Poincare homology sphere. So in a little bit, Xiao's going to calculate the homology group of this and find that it's the same as a regular three-sphere. However, this differs from a regular three-sphere in that it is not a homotopy three-sphere because M is not simply connected. So we show this, we utilize Van Kampen's theorem in order to show this. And from Van Kampen's, we're able to see that our fundamental group of our homology sphere is going to have one generator per node. And then we're also going to have as well one relator per node in our Venn diagram up here. So with that information, what we can do is we can say, okay, let's let xk be the generator that corresponds to the kth node. And then we can get an equation for our relator by the, for each node, we're going to have a certain equation where 1 is going to equal xk, so our generator squared, times xj1, xj2, on and on, however many you need, where our j1, j2, on and on, are nodes adjacent to the kth node. That is getting small. So if we figure out all these relator equations for each node, we're going to end up with this long string of equations. So like, for example, for this first node, we'll take x1 squared. And since it's only adjacent to the second node, then we get that x1 squared times x2 is going to equal 1. We can continue on in this fashion, getting x2 squared, x1, x3 is also going to equal 1. And then this goes on, where 3 is going to have 3 terms because it's adjacent to 3 different ones. And then I'm just going to finish writing this out. Oh, no. x4 is only adjacent to x3. x5 is going to be adjacent to x3 and x6. x6, well, x6 is adjacent to x7 and x5. x7 adjacent to x6 and x8. And then finally we get x8 adjacent to just x7. So we get this whole equation where have a bunch of different numbers or like x sub i's, and they're all going to equal 1 in this sort of relation. And if we did like a bunch of algebra, and we would be able to figure out that we can express this in terms of just x1 and x8. So we're going to write, we're going to have x equal x1, and then y is going to equal x8. So then just skipping over a bunch of the algebra, we figure out that the group that satisfies these is going to be presented as, we can write it as the group generated by x and y, these x and y's, such that x cubed equals y to the 5th, which equals x times y squared. So that's our sort of one representation of our fundamental group. Seems to be not trivial, which we will see. And then in order to relate this to like a group that we actually know about, we can see that if we take A5, so our alternating group, we take the permutation x hat to equal 5, 3, 1, and then the permutation y hat to equal 1, 2, 3, 4, 5. these two are going to, x hat and y hat are going to generate A5, and this also satisfies that x hat cubed is equal to y hat to the fifth, which is going to be equal to x hat y hat squared equal to 1. So then that tells us that this is, in fact, corresponding to our fundamental group. And so because of this, we can find a homomorphism that surjects onto A5. And so since it can surject onto A5, that tells us that, in fact, our fundamental group is not trivial. So, in particular, with more calculations, we can figure out that our fundamental group is going to be equal to the binary icosahedral group. And this group is just an extension of the regular icosahedral group where the extension has degree 60. So basically this shows us that even though we have something that we will eventually show is in fact a homology 3-sphere, it's not a homotopy 3-sphere. And this Poincare homology sphere is the only other 3-manifold with finite non-trivial fundamental group. So this ended up being very important for Poincare in his conjecture because it showed that he couldn't just state it in terms of homologies and Betti coefficients and torsion coefficients, and he needed to involve the fundamental group as well.
I'm going to be going over the homology groups, which doing it the way Poincare originally did is a mess. So there's a relatively easier, more modern way to do it, and it really relies on 2 theorems. One of them is that the abelianization of the fundamental group I use red K.
I think she used
I used
is isomorphic to the first homology. And the proof I'm not really going to go into, but this one allows us to get the H1 pretty easily because our fundamental group was xy such that x cubed equals y fifth equals xy squared. And so the abelianization of this is just if you quotient it out by its commutative subgroup. And the commutator subgroup is, a commutator is just all elements that look like this. Inverse y inverse xy. And you get the subgroup generated by this, such that xy and I guess we'll say pi1. And when you quotient this, it turns out that for the fundamental group here, this is the entire set. So when you quotient it, it just ends up being trivial. And so that pretty easily gives us that H1 is trivial. And the other thing we use is that it's called Poincare duality, and that relates the homologies and cohomologies of the manifolds. So this one says that well, for our purposes, the the kth and n minus k Betty numbers for a closed orientable manifold and manifold. Are the same. So in our case, since the homology sphere is a 3 manifold, we get that one of m is equal to, or is isomorph. It has the same rank. Sorry, it has the same rank because if you recall, the Betty numbers are just the rank of the corresponding homology group. So it has the same rank as H2 of that. And so this, since H1 of m was trivial, H2 of m will also be trivial. That turns out to be equal to the normal 3 sphere. These homology groups are Z for H3 and 0 everywhere.